It's problem number 2 from the 2025 AP Calc AB exams. Calculator question here that presents us with a graph. So the graph has a function f of x defined as a parabola and a function g of x defined as a portion of a sine wave. And we are asked in part A to find the area of the region between these two graphs and to show the setup for our calculation. So if you break this down into 3 steps, slice, approximate, and integrate, if you take a vertical slice of this region, no matter where I take the slice, where I have it drawn, a little further to the left, a little further to the right, the top of every single vertical slice is going to be on the function g of x. The bottom of every single vertical slice is going to be on the function f of x. So the approximate area of this one slice, if I treat it as if it were a rectangle, is going to be the top y value g of x minus the bottom y value f of x times the small change in x across that slice. So that would be the approximate area of one slice. If I want to find the area of the whole region, I'm going to use the integral to add together infinitely many of these slices' areas. So the delta x is going to turn into a dx in its limiting form. The x values that all of the slices that I could have taken range between are 0 on the left end and 3 on the right end. This is a calculator problem, so you can go to Desmos, you can go to your handheld, you can evaluate this integral on the calculator. Be cautious when you subtract f of x. You need to make sure that f of x is subtracted off within a set of parentheses. That would be the one issue that I would potentially worry about with regard to calculator input here. Part B says region R is the base of a solid. At each cross section perpendicular to the x-axis, we end up with a rectangle that has a height given by x and a base that sits in the region R. Find the volume of the solid, show the setup for your calculations. So I'm again going to kind of boil this down into 3 steps: slice, approximate, and integrate. So if I take a slice of the object that's coming off of this region and remove that cross section, what I end up with is a rectangular face. This edge of the cross section would have to fit perfectly back down into the base of the solid from where I removed it, which tells me that this dimension on the rectangle from top to bottom is going to be given by this dimension from out of the coordinate plane, top y value minus bottom y value, which ends up being g of x minus f of x once again. The width of that cross section is some tiny change in x, and they actually provided me with the height. So the third dimension on that rectangular face, this third dimension on that rectangular prism is going to be given by x. So the volume of this one cross section can be approximated by x times this difference times delta x. If I want to add together the volume of all possible cross sections, I'm going to use an integral to do all of that extra work. So this expression shows up within an integral. The delta x is going to turn into a dx in its limiting form. And then once again, the x's that all the slices that we could have taken range between are 0 on the left end and 3 at the right end. Go to the calculator for the value of the integral once again. Be cautious with your input. Again, make sure f of x is in a set of parentheses if you're not willing to distribute the negative into it. Part C is asking us to write but not evaluate an integral expression for the volume of the solid that gets generated if we rotate this region about the horizontal line y equals -2. So y equals -2 would be down here. If I take a slice that's perpendicular to the axis of rotation, that would be a vertical slice once again. And if I rotate this vertical slice 360 degrees about the axis of rotation, due to this gap that exists between the axis of rotation and the near edge of the slice, what I end up generating by rotating that slice is a washer. So with the washer, there are 2 significant dimensions for us to think about. The inside radius, I've labeled that lowercase r sub I, and the outside radius, lowercase r sub o. Inside radius, we've kind of already identified that here. The reason why we get a washer, the reason why we get this gap in the center of our 3-dimensional cross-section when it's rotated is because of this gap that exists between the bottom of the slice and the axis of rotation. So in the coordinate plane, This dimension that I've labeled in red is going to represent the inside radius of our washer. That dimension has to be positive. So to make it positive, I take the top y. The top y is y equals f of x minus the bottom y, which is y equals -2. The outside radius, the outside edge of the washer, is traced out by the top of the slice rotating 360 degrees about this axis of rotation. So in the coordinate plane labeled in purple here, I've got my outside radius established. That's also a difference in y values that I need to establish as a positive. So I'm going to take the top y minus the bottom y. The top y is now y equals g of x, is the top graph here. So g of x minus the bottom y, well, the bottom y is still at the axis of rotation, and that y at the axis of rotation is -2. If I wanted to find the area of the face of the washer, I'm going to find the area of the outside circle, pi outside radius squared, and subtract off the area of the inside circle that's punched out, so pi inside radius squared. I multiply that by a thickness, in this case delta x once more, to turn it into a volume calculation. And in this case, it's the approximate volume of my one washer. Well, if I want to add together every possible washer's volume from this region, I'm going to use the integral to do all of that extra work. So once again, I'm adding together infinitely many of these washers' volumes. So the expression inside this set of parentheses becomes my integrand. The delta x is again going to turn into my differential dx. My limits of integration have remained the same throughout this problem. Left-hand x value where I could have drawn a slice is 0, and then the far right-hand x value where I could have drawn a slice is 3. It does say write but do not evaluate, so we're okay with leaving this as is for part C. And then in the final part of this, it says that it can be shown that g prime is equal to this expression here. It says find the value of x between 0 and 1 at which the line tangent to the graph of f is parallel to the line tangent to the graph of g. So if I'm doing something with a tangent line to f, I'm going to need the derivative of f, which is a very straightforward derivative, just power rule applied here. And then what you have to realize is that parallel lines have the same slope. And if they're tangent lines that have the same slope, I'm looking for the location where my derivative of f is equal to the derivative of g, since in order for the tangent lines to be parallel, their slopes have to be the same. So I'm looking for the value of x on the interval 0 to 1, where the derivative of f is equal to the derivative of g. Calculator's in play, so what I did is I graphed the left side of the equation, I graphed the right side of the equation, and I found the intersection. My window is only spanning the x-axis from 0 to 1, right? That's the only stretch of x values I'm concerned with here. And my graphs are equal to each other at the x value of 0.676. You can truncate or round that to that third digit past the decimal. So 0.676 is okay, 0.675 is okay, 0.67 or 0.68 is not okay.